Okay, hi everybody. Welcome to Rooting on Saturday. This is going to be a recurring thing. For one, it's going to allow me to share some knowledge, my 25 years of making circuits. And another advantage is it will give me a deadline to actually finish some unfinished project. Gotta have the fear, right? So I'm going to be routing several boards over the next couple of weeks. And as far as the format goes, um, please ask any and every question you might have in the chat. Um, I don't mind being interrupted. Uh, if it's a little off topic, I'll probably answer it anyway. If it's very off topic, I might move it till the end. And we have a good 2 hours of routing time now. So let's get started. Uh, what we're routing today is a network switch. Right? Um, these large connectors are M12 connectors. They're basically Ethernet for an industrial setting. So they have they're screwable, so they can't like wiggle out or fall out. They're very robust. They are usually waterproof, which is one of the reasons why we're using them here, because waterproof usually also means dustproof. Um, we have one power connector down here in the bottom right hand corner, and all the rest are Ethernet connectors. Except I believe this one's special. We have 7 that are connected to a switch chip, and then 1 that's going to be connected to a land grid array on the back side, and so we can put different circuits on the back side depending on what we want to do. We could, for example, put just a jumper circuit that would make it from a 7-port hub with one weird one to an actual 8-port hub. It just jumpers the connection across. Maybe I should switch to the circuit to show you guys this better. There we go. Go up to top level. Okay, so we have, let me make this wider for you guys. So we have the switch chip here in the middle with all of its connectors, and you can see one of the ports of the switch chip is going here through a phi to phi connection, which is basically just so that you can connect to Ethernet to get things together without actually using magnetics. We can look at that in more detail if someone's interested. And we have, so that's going into the compute sheet, which is going to be the land grid array. And so we could just jumper that to this, and then it becomes a normal port. We could also put something else on this land grid array, meaning that, for example, we could put a Raspberry Pi compute module on there. That's actually a concrete thing that we're working on right now, so that's why I'm routing it. You could also theoretically put some other kind of switch management. You can see we have the I2C bus from the switch chip going into there, so you could put some microcontroller with it's connected to Ethernet, and then you could talk to the microcontroller and tell it to, I don't know, set up VLANs or be a time server or something like that, right? In which case, you probably would just leave out that one M12 connector. So the concept of the whole thing would be basically a 20-year-old 100 mbit switch, but waterproof and robust, and you can put it outside and you can put it in harsh environments and whatnot, right? So that's the whole idea. Oh, I'm getting a bunch of spam bot messages. I'm gonna figure out how to turn them off next time. Anyway, Um, so let's switch back to the circuit view. So I already placed the M12 connectors because that's kind of finicky and probably not fun to watch. But basically the trick is if you select them, click E. Oh wait, that window's going up where you guys can't see it. Hold on a second. Click E. Yeah, you get the properties of it. I'm not sure if that has to do with German developers on the KiCad team, E meaning Eigenschaften in German. Uh, but anyway, so E gives you settings, and then you can put the X and Y in there, and that's good for spacing things precisely. We have, the connectors are should be 32 millimeters apart across the board. And I also kind of generally grouped things. I guess if I could do a split screen, I can show you guys why KiCad is cool. Let's do that on this side, and then that on this side. And if we go, oh, this is kind of, I had to make my screen smaller for the stream, so this is kind of annoying. But let's say we click on this hierarchical sheet that has the switch chip, and here you can see that it highlights all of the switch chip components. If I go to the PHY to PHY, then okay, that's all the PHY to PHY components, right? So you can use that to kind of generally group them. I already kind of grouped things in, and what we're going to do next is we're going to start with the EMC relevant stuff, right? There's not a whole lot of, I wonder why those little markings are on the PCB. If you select the layer, it sometimes works better. There we go. So the hard part of PCBs is EMC, which means electromagnetic compliance, which basically means, if lightning strikes near you, you're not allowed to break, and you're also not allowed to emit enough interference to mess up other devices. Right? So I guess technically for most things you certify compliance yourself, that you're not doing any of the bad stuff. And but for, if you have an antenna or something, then you're going to have to actually get it tested and get a number from the FCC that you're a compliant device and whatnot. But in reality, it usually means that you, if you're a contract developer or something, I mean, most, at least not most maybe, but many companies sub out their circuit design work to freelancers or other companies like us. And so you want to prove to your customer that you didn't screw it up, because at the end of the day, it's going to be their name going onto it. And so most circuits, most stuff that we ship does get tested in an EMC lab. And so they'll have a big room where they're isolated from the outside world. It's a big Faraday cage, and they'll have your circuit run, have antennas around the room to see if you're emitting something in a stronger, stronger signal than you're allowed to. And they'll also try and break your device with different means, right? So they'll have a little ESD gun that'll simulate people touching your circuit and shocking it, or they'll have a surge and burst tests, or on for the power lines, where it's kind of simulating a lightning strike somewhere close. And depending on what standards you're testing to, those will be stronger or weaker. There's also some stuff that's usually not relevant to normal electronics, like magnetic fields or whatnot. I mean, maybe if you're making medical devices that have some solenoids or something in them that also use magnetics, well, maybe that's interesting. But for this circuit, we can ignore the magnetic field testing part. So we have in the schematic, we have a portion. We have input power connector, and then because people in industrial settings are very good at pinning things wrong, and this is probably going to be wired by somebody to like a battery or something, and so there's a high chance that they could get it wrong. And since we have well, nominee 48 volts input, it's usually more like 60 or 55 or something if you're using batteries, because battery voltage is usually higher than the nominal battery voltage. And power supplies often do a similar thing, just to be similar to batteries. So since we have nominally 48 volts in, we're not going to have a whole lot of current flowing through here. The Raspberry Pi compute module is something like 5 to 10 watts, depending on what you're doing. 5 to 10 watts at 48 volts is not a lot of current, right? So it's not actually all that expensive as far as power for us to just do bridge rectifiers, and they're certainly not expensive as far as chip costs. It costs like pennies, 6, 7 cents. So if we put those in there, then nobody can screw it up, right? So after those two, then we have our, I just called it EMC because that's what it's doing. It's, let me make this bigger so we can actually talk about it. First part of the EMC, and this is if you want to copy this has gone through testing successfully for both consumer electronics as well as things like rail infrastructure. There's higher compliance levels. Yeah, so we have a big TVS diode, the transient voltage suppression. Basically what this diode does is just start conducting if the power across it is above some certain nominal voltage. This is 64. You got to watch out because these things have tolerance. So if you have nominal 48 volts in, then you definitely want considerably more nominal clamping voltage on your diode, because if your diode's 10% low and your input's 10% high, then they might meet each other, right? Often these diodes actually if you have enough power going in, they can destroy themselves. And TVS diodes are set up so that their fail is a short circuit. And so even if they do fail, then they'll just melt themselves together and still keep clamping the input voltage and saving the rest of the circuit. So yeah, so if you have electronics that for some reason died, often just taking off the TVS diode makes them work again. I mean, you may want to replace it with a new one, but yeah, that and capacitors are the reasons why most electronics die. So yeah, that in this case, we want to make sure that if we're in a surge or a burst test, or if lightning actually does strike close to us, or if somebody connected it to the wrong thing, that we just clamp the input voltage to save the rest of the circuit. Then we also want to filter out potential high frequency noise, or any noise really, but low frequency noise, it's usually not so much of a problem. High frequency noise, like maybe we're next to something. I mean, in the industrial setting, one of the reasons why you got to watch that for that stuff is, in an office, say, everything has gone through compliance testing individually. And so if you're on an office desk next to something that has gone through compliance testing, then chances are that it's not going to be giving you a whole bunch of electromagnetic interference. But in an industrial setting, if you're in a machine that's a big metal box, then they only have to pass compliance testing for nothing coming out of their box, right? So they might have components in there that wouldn't pass like at all as an office device, but since it's within their machine, they're going to be they could be interfering with you because they're screwed in next to you, right? That's technically their fault, but that's not a lot of fun explaining, right? And the other thing is, in industrial settings, people weld, and welding is electromagnetic interference on steroids, right? And sometimes they expect you to actually still work while somebody's welding somewhere close to you, right? You know, especially if you're, you know, I mean, we don't have components in welding robots yet, but we may at some point, right? One of these might go in there, and so these next two capacitors are just for filtering out electromagnetic interference coming from outside. They also, you know, technically filter stuff from, you know, coming from us going to the outside, but we're not producing a whole lot. We'll get into that later when we see the power circuit. And then we have the Worth inductor. This is a choke, right? Which basically means it's got both wires wound around the same core. So if we have power flowing this way and power flowing this way, then the two magnetic fields are going to cancel each other out, mostly because the wires are very close to each other, and we won't actually have to go through all the magnetic momentum of, you know, spinning up the field in the core, right? So energy flowing, you know, power flowing in and out in the same amount will pass through easily, but common mode, right? So power flowing in on both lines, which is, for example, the burst test is basically just testing that, right? So let's imagine the wire that's going into this box is going through some cable channel, and there are other cables in that cable channel that go outside and got hit by lightning, right? That's kind of what they're simulating with the burst test, right? Or, you know, maybe it's, you hit the power lines, blocks down the street, and you're still getting some of that, right? Yeah, I got a question. Sorry, I joined a bit late. Is this KiCad? Yes, it is KiCad. I love KiCad. Maybe in some later episodes we can get into why KiCad is basically superior to everything. It's almost as good as the expensive CAD software, but it has the advantage that it's free. That's also an advantage, you know. I guess licenses for CAD software have come down some. Like at the beginning of my career was like, I don't know, 40 grand or something if you wanted to do PCBs professionally. And I guess it's long enough ago that I can say thank God for being able to hack stuff, or I would never have been able to start my business. But oh, and also, sorry, there's a bit of delay. I wasn't ignoring you. It just it takes a bit for the comments to actually go through the system, and then the stream's also on a delay, and so that's why it takes a little bit for me to answer. But ask away. I love the questions. KiCad is free, which is good because that saves you a lot of money, but also it's good because it allows you to share stuff with other people, especially young people entering the field, open source projects, that kind of stuff. Like we have about a continuous two interns that swap out every time one leaves. We'll let another one join, and so you can just give the interns PCBs and they can bang on them without paying for license or anything. We also have student labor, blah blah blah, where you wouldn't pay 15 grand for a license for them to be able to use the software, but you would let them collaborate. And I'm all for enabling young people. I think that's generally amazing. I mean, there's 16-year-old kids that are capable, which I find that really inspiring. So yeah, so KiCad helps that, but also KiCad allows for a not quite a one-touch build system as you would have in C++, but you can definitely do a lot more DevOps with KiCad stuff. You can have like GitHub runners that I don't know, check component availability, create boards. The release process is similar to software. I mean, software has just developed DevOps to the point where hardware DevOps looks like the Stone Age, and KiCad allows you to get a lot closer to what you would have in a software setting, right? Where you have an automatic runner that will make a release out of a Git commit that has a tag in it with a version number, that kind of stuff. Um, we've been talking with a couple of the PCB manufacturers. I talked to JLC at a conference here in Germany, and I guess there's some Americans that want to give JLC a run for their money, which I'm all for. More the merrier. I wish them luck. It's a huge endeavor, but yeah, they also sounded pretty open to. I mean, my view of how this should work is if somebody tags the PCB, and then the GitHub runner should run, and then you get some kind of message. Somebody has to sign off on it, maybe, and then the PCB just goes out algorithmically to the production, right? Because then you can be sure that the thing that got produced is actually the thing that you marked as release, right? Nobody jumbled the version or something. And yeah, the CAD's not quite there yet. Like there's things like component rotation and stuff that's not quite in the build. We'll get to that in a minute when we route the rectifiers. Yeah, the Chinese always get confused which we produce in China, but it's not a knock on Chinese people, but they're the ones that make all our circuits. So they get confused whenever there's rectifiers used in a non sort of or AC way, because it's not clear what side the plus and minus output should be on and how it should be rotated. And I actually also rotated the footprint wrong, so that confused everyone. But yeah, so we'll get to that in a minute. But yeah, there are some gaps in the amount of information that goes into the design and therefore is transferred to the producer, which maybe need to get filled before you can actually just have a one-touch, an actual one-touch build this thing that actually builds a physical thing. That would be awesome. Anyway, so coming back, to the other half of the circuit. So after we go through the choke, right, which is going to stop common mode current, we're going to clamp again, which is probably overkill, but theoretically, depending on what kind of loads are going through this inductor, we could be consuming power at its own self-resonant frequency, right? So if we consume power like on, off, on, off, on, off, on, off, on, off, and that in the exact frequency that will allow allow the inductor and capacitor combination that we have on here to kind of become a seesaw, right? So every direction it increases power flowing through and into the capacitors on the other side. So to make sure that doesn't ever happen to the point where it creates too high of a voltage by swinging back and forth, we have the second clamping diode, and we definitely don't need as much power here. But since we already used the same component on the other side, yeah, we're just using it again, just so we don't have a big bomb. Big long bill of material lists are no longer as much of a problem now that it's semi-automated. But if you're using non-standard components, which most of your components are going to be, because there's 30 million components or something in the world, so the chances of it being already set up on the production machine are very low. So yeah, I mean, JLC is insanely cheap in my opinion for charging you something like $3 for every new kind of component, and then you're also buying in smaller amounts. So it doesn't really matter as much anymore as it used to use the same component again and again. But yeah, I did here, maybe out of laziness. Also, I could have saved maybe 10 cents on that part or something. We're not producing that many of these switches yet. That was good. That's really going to make a difference. I find it amazing anymore that oftentimes the circuit is not the majority of the cost, right? Like we have one product where the the circuit's like $30 or something, and then it goes in a box that costs 60, and then it has connectors to the outside with sensors on them that cost hundreds, and then it comes in a spiffy case, briefcase thing. It costs hundreds, and it's like, well, all that for a $30 circuit. Yeah, and so we coming back to the topic, I'm jumping all over the place. Sorry. So we have our choke L2, which will suppress common mode interference. We also could potentially have differential interference, right? So one line or power going one direction on one line, the other direction on the other line, and we don't want to admit that. That's going to probably be coming from our buck regulator, because connected to this in the next sheet, there's the buck, which turns 48 volts down to 5, right? And so it's going to be switching on and off, and that's potential interference that we don't want to give to the outside world. It creates too high of a voltage by swinging back and forth.
Wait a minute, I'm hearing myself.
Clamping diode, and we definitely don't need as much
Why
power
am I hearing
here.
myself?
Let me see. Hold on. I'm new to this whole stream thing. Sorry. Okay, that's why I'm hearing myself. No longer hearing myself. Yay. So L3 is going to suppress the differential mode interference, and I guess theoretically you would put another capacitor on the other side, but we also have the input capacitors to the buck regulator, just right in the next sheet, which is why we're not seeing it here. Right? Okay. So that's what we're going to route first. Let me. Oh wait, you guys couldn't see my mouse for that whole time. I hope it was clear what I was talking about. Yay! Odin doesn't know how to stream yet. Okay, so we have here is our power input, and we don't have a whole lot of space because we do have to put a lot of components on this board. So I'm going to be a little space skimpy here and set these things up to where they, let's see, so we want power going, I guess we could do the filter thing on the right hand side of this. And then just set two of these up here. So these are the rectifiers. Now the connector is actually coming at us up from the board, and so these are technically both of these components are on the same side of the board, but the connector has feet that are like, I don't know, 10 or 11 millimeters tall or something, and so these components will fit under the feet easily, and the connectors are going to be hand soldered from the other side, so we don't really have to be careful about being close to the connectors here. Even though it does look very sloppy, it actually will work in practice that these are connected this way. So I probably want pretty big tracks. I guess it doesn't really matter, but because in the case of surge or burst tests or something, I mean that's going to be the most power going through here. It takes a while for the tracks to get heated up. Okay, so I guess I went a little too big. MIOCD is going to make me make them all small again. In KiCad, if you click a track and then hit U, then it will select the entire track. So that's the entire length of it, at least to the next via or something. And you can also hit UU if you want to do really the whole thing, even across layer switches and whatnot. So we got both of these coming together, and then I think we're going to do the rest of the EMC stuff later. Oh, okay. This is a common mistake I see in people's circuits. If I have this clamping diode, right? So thinking back to the circuit, this is the next thing in the line. Clamping diode's supposed to make sure that the power or that the voltage gets clamped down to whatever its maximum voltage is, right? So if I were to connect this up like this, doing it wrong here just to show, right? So this is, or or I guess it's not wrong yet, but it will be in a minute, right? Okay, so theoretically, if I connected this up, this is going to clamp, and we're going to put our capacitor. If we were to put our capacitor, say, here. Oops, well, that's going to be the wrong way around. But if we were to put our capacitor here, what's the problem? Let's see, do I have a show of hands thing? I'm going to have to figure out how that works so I can do ask show of hands. So this, oh, I have another question in the queue, but I'll get to that in a minute. Let me finish this thought. So if I were to put this capacitor here, we might actually blow the voltage rating on this capacitor in this constellation, because even though the diode up here is clamping, it's clamping at its connectors, right? And so if we have a very short-lived but high voltage peak coming in here where we got, I don't know, 2 kilovolts or something, well, those 2 kilovolts are going to drop across these PCB tracks, right? So here at the pin we'll have 2 kilovolts, just say for the sake of argument, and that's going to fall off. Maybe over the diode we lose 100 volts or something on down the line. We still could be more than 250 volts right at this capacitor, right? I mean, it depends on the components. Some components, if getting hot is your problem, then you're probably fine, because the things like ESD or burst are so short-lived that you just won't have time to heat up, right? But if electrical breakdown is your problem, as is the case in a capacitor, then yeah, you really don't want to exceed the maximum voltage, even for a very, very short period of time. Right. So the right way to do this, or I guess maybe one more example of doing it wrong, which I see in practice a lot too. Maybe there'll be a via here, and then someone will be going off somewhere. Oops, switched layers. There we go. We'll be going off somewhere else. Yes, you have a clamping diode here, right? But it's not clamping the voltage that gets to this wire, right? So if you look at boards that don't pass EMC for reasons of over voltage, then this is usually what they're doing wrong, right? So the way you actually have to do this is you make everything that's comes after the clamping diode, you make it go through the clamping diode, right? And then there's no way for the voltage to exceed limits. Oh, this is kind of frustratingly close here. Okay. Should I maybe change this up so that can fit there? I have no idea how much I'm going to be space constrained eventually. So let's just error on the. Another KiCad trick, if you press G, well, on top of a component, you can move it with tracks, right? And if you get into problems, then it'll turn green. So yeah, that makes moving components around actually a whole lot easier. Doesn't quite work as well as I would like. I think there's probably another version until it's actually super good, but I'm already happy that they implemented it in. I think it was actually 2 versions ago or something like that, but I was very happy when they did. So yeah, let's see. So why don't I just delete those and then move it? Oh, still there. Now I'll just boot it all new. Like with software, I often kind of iterate on the design, like root a little bit and then take it back just to see how much space the routing took and whatever, and so I can visualize where things need to go. You can also hit G on the sorry, hit D on the end of a track, D as in drag, and then drag it into places. Also makes you a little faster. Okay, so we want to clamp here immediately, and then after the clamp, everything will be clamped. Coming up through here. Now these tracks are a millimeter apart, and that's sorry, not a millimeter apart, a millimeter wide. And so that's plenty for the amount of current that we're expecting to go through here, right? It's giving a couple hundred milliamps, right? It's not going to be much. Oh yeah, I forgot the question. The key question is how many layers is the board? Board is 4 layers. I usually don't do stuff that's more than 4 layers. I mean, I guess I have I've done some higher layer boards, but that's usually more sort of high um, high pin count things like connecting a processor to RAM or something. You may need a lot of layers. Like if you're making a cell phone, obviously you're going to need a whole lot of layers. But for the industry is still for all intents and purposes old. I mean, a lot of the stuff that we make goes into the industry side of things rather than consumer electronics. Because consumer electronics, you have to be set up to make millions, if not billions of them. Well, I guess maybe not too many products reach billions, but tens of millions of them. And we're a small company. We're just not set up for that. We do out of house manufacturing for everything that's more than maybe uh, 10,000 a year or something. That's kind of the upper limit of what we're going to do in house. And yeah, so that kind of I mean, people don't realize how much engineering work goes into the machine that builds the machine, right? Like, um, the current project is for industrial ovens that I'm working on, uh, um, and just the amount of effort that goes into making sure things get baked properly. Things like ceramic coatings or soldering or whatever, right? Um, the amount of effort that goes into that is just amazing, right? And normal people don't see all of that engineering work, and so that's where most of our stuff goes, right? So um, yeah, so in that setting, like 2 layers is probably enough, but only probably. You have to think about it. Like, am I getting ground here well or whatnot? And with 4 layers, you can do ground and power on their own layer. And then that also greatly reduces your EMC, interfere stuff for non-connected to the outside parts of things, right? Because you have a 2 layer board, then and you have a wire that's switching on and off fast, and therefore emitting some signal, then that could possibly be a problem. But if you have a ground layer like right next to it, then it's just going to be moving around electrons in that ground layer, and that's from farther away, those two will just cancel each other out, the movements in the wire and the ground. And so, yeah, you're not going to be emitting anywhere near as much signal from that. And so, yeah, so 4 layer boards make make I mean, they're only marginally cheaper at this point, marginally more expensive at this point, and it saves you a whole bunch of headache and generally yields a better product, right? So yeah, so this will be a 4 layer board. That's kind of the usual thing that I use. Okay, let's see. So I think I got through all of the comments. Those are just bots. Man, bots are a problem. Uh, okay, so if we switch back to this, it doesn't actually really matter in which order I do these, but it's a little more clear if I do them in the same order. Um, so if I want to do this one next, then if I click on it here, it'll be highlighted here. And so there we'll see it wasn't the one that I would otherwise be doing next. So that's good. I checked. I have a high grid. Yeah, I have a relatively high grid. So I'm going to make this so I snap a little closer. With modern pick and place machines, you can actually put components really close together. It's not as fun if you're hand soldering, but I'm pretty confident that I'm not going to have to mess around too much with a soldering iron with this design. Um, so I'm just going to put the components really close to each other. And that way, I'm going to end up with enough space. I'm probably going to end up with a big piece of space when I'm finished, where it's like, oh, well, you didn't have to make everything so close to each other. But I'd rather do that than having to move a bunch of stuff around, right? Okay, so now we want this big thing, and I'm pretty sure this will fit under the connector, but I don't really want to. I don't really want to have to find out that I was wrong about that. And it does, like it's let me see if I have a data sheet of this thing that I can slide in so you can actually see what I'm talking about. Um, so it has these pins up on top that are conductive. And so, yeah, I really don't want that touching the connector. Um, so let's just close this. Yeah. So I'm going to put it next to the connector there. We can connect this up into there. And then we have on the other side, we have our EMC. Yeah, okay, that thing probably should be next, because if we have high peak voltages, they're going to be happening next to the inductor first. Let me know. I don't know if did a good job explaining why this thing needs to be part of the circuit. If I didn't, then somebody please ask a question and I'll draw it and kind of explain it. Um, yeah, I mean, if you think back to like Electronics 101 or whatever book you started with or whatever, I'm sure there was like an LC circuit where you uh, where you had an inductor and a capacitor on both sides, and then moved current back and forth through the inductor, charging one of the capacitors, discharging the other, turning it into magnetic motion, magnetic momentum in English, right? Yeah, magnetic momentum or more magnetic energy, and then back into a voltage difference in the capacitors, and then back into magnetic energy. And it's if you have some circuit which is pulling in the right direction at the right time in the right frequency, then you can get it to seesaw up to some some high voltage, right? You keep putting energy in. Right? So, yeah, this is what makes electronics hard. Thinking about those kinds of bugs that could be in your circuit, because the first time you test it, even if that is a potential potential danger in your circuit, you may not see that in testing, and conceivably you could not see it for years, right? Like there could be component tolerances that means you never hit that exact frequency. It could be temperature dependent or that kind of stuff. So yeah, that's why the analog side of electronics is hard. Okay, so here these should be pretty clear. We have three capacitors that are have different values, which means they're going to be dampening different frequencies. And oh wow, why did I put those next to each other already on purpose, or why are they all next to each other? Anyway, so let's see. So I think I'm going to try and do power here. So if we kind of snake around in an S shape here with the circuits, I mean the inductor for the buck is really tall, so we definitely can't put that under the connector, but these little guys are not that tall, so there's no problem there. Oops, what did I hit the wrong key. Yeah, let's just go across here, and then we can go up again in a minute if we want to, or to get to the rest of the circuit. And another thing that one may kind of want to watch out for with the things going to the outside. If you have electrostatic discharge, or you're in surge and burst testing, these gaps could be somewhat interesting, right? Um, since this is, yeah, I mean, if that were to short, it would short to a different clamping diode, right? So that is actually, in this special case, probably not a problem. Um, I guess maybe. I mean, the thing is, even if something's not a problem, people thinking it might be a problem can also cause unneeded effort. So why don't we just make that obviously not a problem? And we actually probably need to go a little further if you want it to obviously not be a problem. There we go. Oops, hit G instead of D. It does other stuff with G. There we go. Yeah. Also, now that we're past the common mode filter, we don't have any more inductance in the ground path. We're going to start doing ground plane under here. Um, but here, I want to make sure that they're all low ohmage connected. So yeah, I'm still routing, but at some point I'm just going to stop routing ground and let the copper fill take care of it. Right? Okay, that's a little dude. Also, at some point we can stop with the super wide tracks. So yeah, okay. So I guess yeah, we still have this one. Still have this one. This is, I think, not quite as tall as the other, so it theoretically could go under, but I don't think we really want to go under that. If we would just went like this, then that would put everything in somewhat contained space. Yeah, okay, and then we have 48 and ground right next to each other for the capacitors for the next portion. So we're done with that sheet. So that was this sheet here. Now we want to go to the step down sheet, and here we have just a bazillion input capacitors. And the reason why I did a bunch of ceramic capacitors in parallel here is, for one, because electrolytic capacitors don't age as well, especially at warmer temperatures. I mean, the electrolyte in the capacitor is actually, a liquid thing that can cook off, right? So that's one of the reasons why it's often the bulk capacitors in design that will fail first, because the electrolyte cooked off. And if we look at bulk capacitor ratings, like the aluminum electrolyte capacitors, 1,000 hours at more than 70 degrees Celsius or something is the common rating, and then sometimes you'll get like a 3,000 hours, or maybe you get a 3,000 hours by 85 degrees Celsius. That's already a pretty expensive one, right? Um, and yeah, I mean, we had actually one, the previous version of this network switch we had installed outside on an industrial cooling thing in the sun. In a metal box, also producing its own heat. You could imagine this PCB getting up to somewhere near 70 degrees, and that's just going to really lower the lifetime of the electrolytic capacitors. I mean, most components on a PCB don't really age, right? Like ceramic capacitors, they get a little moisture, sleeps in, and changes them a little, which is why, back in the day, there was the urban legend of just bake your graphics card when it stops working properly. And that actually, there is some logic to that. You're baking the moisture back out of the capacitors. But since we kind of over engineered most of the capacitor stuff on here, that shouldn't really be a problem. I mean, ideally these things should last a long time, and like a transistor, if you're not abusing it, will essentially last forever. I mean, probably not forever, right? Forever being something like 100 years or something. At that point, the robots will have killed us all, so it doesn't really matter. But an aluminum electrolyte capacitor is not going to last. I mean, in most cases, it's not going to last 10 years, even if it's in a nice, cool environment, right? It, often with consumer electronics, that's the thing that breaks after 2 years, right? So we don't want to use those. But with the high voltage of 60, 60 volts, potentially 48 nominally, um, we uh, it's hard to find ceramic capacitors that go up to that voltage. Because I mean, the trick that they're using with ceramic capacitors, and the way they manufacture ceramic capacitors, at least in theory, there's probably some really weird ninja stuff that makes it's going to make me totally wrong. But in my head, how they manufacture ceramic capacitors and how at some point they did was deposit a layer of ceramic, uh, um, deposit a layer of metal powder, laser the metal powder so that some part of it stays, brush off the rest of the metal powder, lay down a layer of ceramic, lay down another layer of metal powder, laser it again, right? So you can have really, really, really fine structures inside of the ceramic capacitors, which, the capacitance increases the closer you can get the plates together, right? Um, so, uh, as you increase voltage, then you also increase the spark gap distance, the gap between the plates that you have to have so that there's not, the electricity doesn't spark and jump through the gap, right? So by increasing the voltage of the ceramic capacitors, they actually have to increase in size pretty seriously. And so at um, at the high voltage, you're going to have bigger capacitors, but then also you have it's called derating, right? So a 4.7 microfarad capacitor, or ceramic capacitor, is going to have 4.7 microfarads at 1 volt charge, right? And then when you start increasing the voltage above 1 volt of the actual charge, uh, the capacitance is actually going to go down. I realize I'm probably not going to be able to explain why that is, but that is, right? And it is a little different between different manufacturers, but generally, with these 4.7 microfarad capacitors, when I charge them up to 48 volts, I probably have maybe 1 microfarad or something of actual effective capacitance at that value. I mean, that's why you never want to use just normal um, ceramic capacitors on like analog circuits, like filters or something. So if you're doing like a, I don't know, a low pass audio filter or something, and you're using a ceramic capacitor, then uh, depending on the voltage of the audio, it's going to dampen it more or less, right? So you're going to like dampen the upper side of the sine waves more than the lower side or whatever. So yeah, uh, don't use standard capacitors in that kind of thing. And in if you have higher voltages, then be careful with derating because it can be wildly different than you expect. I mean, there are some capacitors that have like an 80% derating at higher voltages, right? So yeah, so that's why I have so dang many of these things, because I want to replace a relatively large bulk capacitor with something that will age better and also withstand better heat. Vibration is also a problem for electrolytic capacitors because they have like these thin foils in them, and if you kind of vibrate those a lot, then it can be problematic. I mean, vibration is theoretically also a thing with ceramic capacitors, but not to the same extent. And yeah, I mean, we did do a project for rail infrastructure where we really had to worry about vibration constantly forever, right? And yeah, that can get interesting, especially with components like electrolytic capacitors. So that's why there's so many of them. That took a while, that tangent. um, so this is just a big block that's going to it's going to stabilize the voltage of the input of this buck regulator. I guess there might be people in here that don't really know how the buck regulator works. We could look into why I'm doing what I'm doing. Let's use this and get rid of. Oops. Oh, no, that's not what I was looking for. Let's get rid of this so we can draw on it. I guess I theoretically have a trusty pen which I can draw with. Let's see if I can draw better with a pen. Okay, so the buck regulator is, oops. There we go. Buck regulator is basically a input capacitor and then a switch and then an inductor. Wow, I really can't draw today or ever. And then an output capacitor and then a, oops, I drew that wrong. Where's the eraser? There we go. We got another ground here, and then if this ever gets below ground, because it's pulling electrons that way, right? Or I guess technical current direction, right? I mean, the electrons are actually going the other way, but that's confusing. Damn Alessandro Volta. Okay, so if that ever gets below 0 volts, then it goes through this diode, right? So you have either the switch is on. Let's do switch on in red. Then you have energy flowing like this. And in order for energy to flow like this, you're going to have magnetic momentum building up in the inductor, right? So the inductor is going to act as a resistor, but the energy that it's taking away in resistance is not going into heat. Some of it is, but most of it's going into magnetic momentum. And so the magnetic momentum builds up, and then we'll do the other one in blue. In blue, the switch is open again, right? In which case, magnetic momentum is going down. Let's just represent that with an arrow going the other way. The magnetic momentum is going down, so magnetic momentum is being turned back into current, right? So current is still flowing this direction, but this is not connected to the input anymore because the switch is open, which means the voltage at this point, right? If you're taking current out of this end of the inductor, if you're taking electrons out or putting them in, if it were. I hate that it's the wrong way around. Anyway, so you're putting electrons into this end of the inductor, right? Current is flowing flowing the direction of the blue arrow. So the voltage is going to have to go down, right? Because we're putting electrons in. So the voltage here is going down until it gets below ground, in which case we're going to have current flowing through this diode into the output capacitor, right? So I guess you can't really see my mouse so well here. Right here, the output capacitor. And so you go from a higher voltage input that gets turned on and off and on and off and on and off, and whenever it's on, then you're turning the voltage difference into magnetic momentum. And whenever it's off, you're turning magnetic momentum back into voltage difference that pulls through the diode back around in a circle, right? So that's how a buck works, right? So we have two circles of energy that we have to be mindful of, right? We have one where we're going like this, and one where we're going basically like this, right? Those are the two circles. So when we lay this out on the circuit, then we have to make sure that those two loops are tight, right? If you will, the more surface area within the loop, the more parasitic inductance and the more interference and whatnot you're going to have in your circuit, right? So if we look at this here we have the inductor, right? Here we have the output capacitor. This is just feedback so that the chip knows what voltage the output's at, right? So that's not interesting within the power side of things, right? Here the diode D7 That's the diode that we're going to be pulling energy through when the switch is off, right? And LX to VCC, that's where the switch is, which is inside of the controller chip. I mean, there are buck regulator controller chips that have the switch outside. It's easier to have the switch inside, right? So yeah, but for it's usually for smaller power. You're gonna have an internal switch, and if you're gonna do big power supplies, you're gonna have an external switch because you have to get rid of the heat. And at some point, you probably want to manufacture it in a different with a different technology than the rest of the circuit. The rest of the circuit's going to be pretty standard digital electronics, whereas the switch, I mean, at some point you might want to use a gallium arsenide FET. We can get into those topics later if anybody's interested. But for the purpose of this buck regulator, we have one loop flowing from my giant array of capacitors here through the chip into the inductor into the output capacitor, and then the second loop is flowing basically from the ground of the output capacitor through the diode, through the inductor, and then into the plus side of the output capacitor, basically, turning magnetic momentum into voltage stored in the capacitor, right? So let's look at this on the board. Here we have the inductor. The inductor I know is too high to fit under the connector, which is why it's great that we have room for it to be not under the connector. I think I'm going to lay this out like outside of the board and then move it onto the board. So here's our diode. Where's our output capacitor? Okay, there's our output. So we basically have one loop now here. We'll see if this actually works when I put the chip next to it. But theoretically, if this is our loop, oh, I want to be top louder. There we go. If this is our loop, well, that's about as tight of a loop as we can have, right? Here the in the off phase where we're turning magnetic momentum into voltage in the output capacitor, then this is basically a perfect loop. We'll see how the chip actually fits into this. This should be the chip in there. Okay, so, oh wait, sorry, I'm going close to the wrong thing. So we're interested in the switch. We're interested in ground. Maybe like that or something, I guess. It depends on where. Where our giant capacitor array is going to go. Does that fit like this? No, it's going to have to probably go something more like this. Okay. Okay, maybe I want to lay it out like that, in which case this would go, oops. Okay, so this would be the switch. Yeah. I mean, this would give us the second loop going from, I mean, I guess if I put a bunch of vias here, then it'd be relatively low ohmage to ground. I mean, if I didn't have a whole bank of capacitors, if I had like one capacitor, I could definitely get this loop tighter. But we don't really have to worry so much about noise created by us in this context, because we're in a metal box and all the other components in the box are on the same plane, right? So there's a bunch of ground layers and kind of in the way. And then you also want to worry about noise going from you to the outside, like to other components that are on the other end of the wire. But we have our, our big filter circuit there. Oops. Although maybe I want to take this and rotate it so that, oh, the inductor's in the corner. I mean, it is a shielded inductor. Like you can have interference going between two inductors next to each other, right? Because one makes a magnetic field and the other turns magnetic fields into voltage. That seems logical that they can interfere with each other, right? But this big inductor is shielded, which basically means that there's a magnetically conductive metal around the core. So we don't really have to worry about interference there because it's mostly just optics. But if we have 48 volts here and ground, then we it's kind of a pipeline, right? We have unrectified, then we have rectified unsafe, then we have safe, then we have a bulk input storage, and at the end we're going down to 5 volts. I mean, that kind of seems logical to me. What are these? Why are they so big? Let me check the... Oh, so there are more than just... Okay, more than just the normal bulk input. Let's see where we put those guys. I think we could just put them at the end of the line. And just 4.7 like everybody else. Not quite sure why that was set up that way, but put here and then move the whole line down. I think I'm going to try and figure out how we can, if I can maybe do like a stream and Twitter Spaces or X Spaces kind of a thing, to where people can actually talk to me with voice. It's kind of lonely just talking into the void and now and then seeing people's comments, seeing a whole lot of bot spam comments. Yeah, I mean, I would like to make this more of a format of just people hanging out talking about PCBs while I work. Okay, we definitely have a bunch of other random... Wait a minute, what is this guy? What's this guy? Well, he's also just... Okay, so there were just some rogue ones kind of floating around. I'll just add it to this. Okay, and these are probably just the red... Okay, that, I think, is the 5 volts to 3.3. We don't actually consume a whole lot of power at 3.3 volts. It's just the networks, some of the network switch and some of the power or Ethernet controllers. Oh yeah, the switch is also going to be a PoE switch. I forgot to mention that earlier. But yeah, PoE is a godsend for industrial stuff because you just have one cable and you can't plug it in wrong, and everyone's allowed to plug it in. And that's a big thing on in industrial setting is like, is someone actually allowed to change it? Like, you have to have certification to connect things together that are higher voltages or whatnot, where you get it wrong. Whereas network, everyone's allowed to connect a network. The intern's allowed to connect a network. Like there's no rules against that, or no like OSHA, I guess is what it's called in the US. But it's gazettes. Anyway, let's call it here. So yeah, there are no rules against that because you can't get it wrong, and you can't, like 48 volts was not going to hurt if it shocks you. Like you don't even feel it, and it doesn't do any damage. And yeah, so if everything is 48 volts and you can't get it wrong, then people don't realize the installation cost of a lot of components far outweigh the actual cost of the component, right? Like, you usually don't have a, certified electrician automation-y dude running around in your facility. I guess if it's a huge one, maybe you do, but for, a normal shop, I don't know, maybe they're soldering PCBs, maybe they're, I don't know, making insulation for walls or whatever. They're not going to have the right guy running around, right? So if something needs to be connected, then somebody actually drives there, and there's this whole class of relatively qualified, sometimes highly qualified engineers that spend most of their lives driving places, and that seems like such a waste to me. I mean, yeah, like if you have a software thing that's not working, then yeah, and you're a normal consumer, then somebody from a call center will help you, and they'll just SSH into your machine or whatever the remote thing on Windows is called. And yeah, they don't have to drive to your place. Whereas if things are not trivial, then in the industrial setting they do have to drive, and yeah, it's a huge waste. So we want to make the world more efficient, right? Okay, so we got a bunch of this kind of stuff. I think we probably want to make sure that the feedback, like the question is, which of these components do I want to prioritize in its placement? So we have I think it's called a snubber here, which basically needs to be routed pretty close. We can maybe get into what the component actually does some other time. I think we probably want to, well, that's weird that they made it that way. How do you guys expect me to do this right? I guess we're just going to put it here. And then via our way through. I like putting components in just lines of stuff. Okay, so these two, we probably want these two to not be in some giant loop, because if you look at the values, right, 500 kilo ohms, then if we have this part being a giant wire with capacitive coupling to other stuff, then we could definitely induce some ripple here from some other source. And since we also have a source right next door, this big switching loop thing, then yeah, we probably want to keep that middle part quite short. Wait, no, this doesn't seem like the right one. Oh, this is enable. I'm talking out of my ass here. These are the ones I meant, right? Oh, and with this one, these are actually much lower values. That's odd. Modern regulators, these are usually way higher ohmage, but I'd imagine these are low ohmage because there's probably some older. I mean, going down from 48 volts is not a space where there's a lot of recent innovation, right? I mean, you want a 5-volt regulator, you're going to get some insane GaN FET thing that'll work at megahertz, so you can use a cheap inductor. Like if you go back to the drawing, how fast this part needs to turn on and off is going to depend on the amount of energy saved that can be stored in this inductor, right? So if it turns on and off slow, then you're going to need a bigger inductor to be able to store that much magnetic momentum. Bigger means more expensive, right? So if you can switch on and off really fast, then you can use a much smaller inductor. But that also means that your diode needs to have a turn on time that's really quick, and you're going to be switching with a field effect transistor probably. And in the modern chips, they also put a field effect transistor down here too, rather than the diode. So they switch the one on, the other off, and then back and forth. And it's more efficient because you don't have the voltage drop over the diode anymore, right? And if you could switch really fast, then it starts to become really efficient. But this is probably an older one because, yeah, like I said, I mean, if it's nominally taking 48 volts input, then you got to be able to expect like 60-ish for your clamping stuff. Our clamps are nominally 64, and so if they're nominally 64 and they have 10% tolerance or something, then you definitely need a buck that will be able to stand 70 something volts on its input, just to be on the safe side. So yeah, those are kind of hard. I mean, they're not impossible to find, but they're harder to find. So which is probably why this is an older one, which is probably why the resistors have such low resistance value. But that also means that we're going to have less problems with this wire going up and down. But again, that took me several minutes to say. The next person looking at the circuit is, if we do a big loop here, they're not going to understand that that's okay because the resistors have lower resistance, so it's going to be less ripple at the same parasitic capacitance, blah, blah, blah. Let's just make it small, and then nobody ever has to ask, right? So we got 5 volts going to feedback. Well, 5 volts can be far. That doesn't matter. That's going to be a plane anyway. So we want the feedback to be small. The other feedback one's here. And so we're going from ground. I guess I could do it that way, round. I like putting these in rows because it just looks better, first of all, but also if you can then put like spaces at the end, and then this distance small and then this distance larger, makes it easier to like hand solder them, and yeah, just generally reason about them and put down silk screen and whatnot. Okay, so what else is important? I usually try and go from like the more important stuff to the less important stuff. I'm not actually sure what this is. This is probably some, this is probably some like internal timing thing for the chip. This is probably some settings thing. Enable that doesn't really matter. I mean, even if it ripples, there's going to be some, it's going to be a Schmidt trigger, right? So it's going to have some hysteresis in the switch. By the way, if I'm using any terms that people are not familiar with, just throw it into the chat. It's not uniform what terms people know and what terms people don't know. I mean, between two different cliques of people that talk to each other a lot, they're gonna all know the terms that the other people use, and then you go into a different bubble and it's complete different terminology. Sometimes they'll have, two terms for the same thing, right? So yeah, so if I'm using some jargon, then definitely ask. Don't be shy. It's fine. It's probably my fault anyway because I'm probably using some obscure term. Uh, yeah, so let's do these next by virtue of, I don't know off the top of my head what they are. Oh, they're already next to each other, I think. R23. Yeah, okay. I guess I could also just select both of them. Okay, and then that's actually also logically the next thing in our line of. Oh, but that also means that ground is not going to be ergonomically there because I'm going to have a wire going across there. So why don't I switch this around anyway, and we'll just use ground from the outside. And 5 volts. Okay, I got 5 volts over there. I could even like sneak it through the inside of the. Oh, what's up with that? Snapping the grid in a different. There we go. Okay, well, why don't I put down some tracks just to make sure I'm not crazy here before I do the rest. Feedback is not going to be, there's not going to be a lot that's flowing, so we'll just use a 0.2 millimeter track. I think 0.08-ish or so is, anything below that's going to get really expensive really quickly. And JLC keeps changing their mind of what the smallest track is on a 2-layer board before you have to pay extra. And I think that's like 1.37 or some weird number like that. That probably has something to do with the Imperial system. But I generally have had the experience of, unless you're really space constrained and have big buses with a bunch of wires, and point two is a good width. Like, especially if you're doing prototypes, you might need to like hand solder some stuff off the board and on the board again and blah blah blah. It's pretty hard to damage a 0.2 millimeter track to the point where it doesn't work anymore. Whereas if you're looking at like really fine ones, then I don't know, you scratch it with the soldering iron while you're soldering something. You can break them with a solder tip and that kind of stuff. Yeah, so I usually just go with the 0.2. I mean, back in the day, it was the finest that certain manufacturers could manufacture. But yeah, okay, this is just going to ground here, so we'll just put that in. I haven't actually done the plane yet, but when I do the plane, that will connect to the plane. I guess I could just go through the, wait a minute. Oh, VCC is not 5 volts. Okay. Yeah, but that's fine. I can just do via here and then go over there. Okay. Then we have this guy, which is probably some speed, frequency setting resistor or something. It's been a while since I've looked at this buck in any detail. I mean, it is my circuit. I designed it a while ago now, so I don't remember off the top of my head what everything is. Okay, and I want to do these guys, do both of those. Oh, that actually works out even better than I expected it to. So this one's to ground, so let's put those ground guys next to each other. And then you probably want to move this all up a bit. Let this fit under there, and then we don't have to move that one away. Weird grid snappage again here. Sometimes it helps to, yeah, there we go. Use the different pin. Okay, that's to switch. Yeah, that kind of can just stay like that. Okay, I think that's all the components. We'll start routing, and if anything goes wrong, then we'll just know. Okay, I think I'm going to do the one big track going 5 volts. I mean, somewhere here is where we're going to put the land grid array for the big chip, for the compute module or whatever. So that's where most of the 5 volts is going to be going to. And then, yeah, so we'll just leave 5 volts up top there. And VCC, that's definitely not going to be a huge, I mean, that's going through resistors. There's not going to be a lot of power flowing on this one. So maybe we just do it like this-ish. Or I guess I could just do that as a track. There we go. W selects everything. There we go. I could just go like that. And then, what else we got? That's just ground. Why are there stuff going up there? Oh, that's just stuff passing through. Put it there and then it won't confuse me anymore. So ground, definitely some vias in there. Let's see, that's the output capacitor. So why don't we put even like more vi? Why don't I put the ground plane down? Okay, plane, so we probably don't want to include any of that. So we'll probably want to start here with the plane. We want it on top, that layer. So I'm going to probably use N2 as power, and then all the rest of the layers are going to get a ground plane. One thing that wasn't entirely intuitive to me at the beginning was if you use a plane on one layer, you're probably going to want to use a plane on multiple layers. Why is that snapping to that? Okay. You probably want to use a plane on multiple layers because the amount of copper deposited on a layer should be somewhat uniform. And so if you have a layer with only a very few tracks and then a layer with just ground pour through the whole layer, then you might get like copper bleeding between the tracks, just because like they'll set up the time in the galvanic bath according to the amount of copper that they want to attract out of the water, or whatever solution the copper is dissolved in, and so or I guess no, they're probably going off. Yeah, so they start with copper plate and they're etching it off into acid, right? And so they're gonna if you have big planes, then they don't have to etch off as much copper, and so it's going to be in the bath for less time than if they have to etch off most of the layer. And so, yeah, if you mix and match, then could be that you leave some extra copper on. I mean, it doesn't happen much. It's happened to me once in my career, but yeah. Okay, we could do that one thick. Let's do ground as thick as we can. Let's see, we probably want to just play around with some vias, get the stuff all well connected here. And that already has all the vias because of their thermal vias. So that's going to try to route all of this. I think I'm actually going to go all the way really close to that so that we don't mess up the ground plane. And we probably want to do thick across here. This is probably totally overkill, but oh well. Make sure these guys are well connected to ground. Okay, I guess I probably don't want to do a 48 volt layer, which means I really need to connect these guys well to each other. Why was there already, is there already a track there, or what the? Anyway. So, I guess I'm going to do like a couple of lines going through, like maybe every other one gets connected to the other side, just to make sure. These are all pretending to be one giant capacitor rather than a bunch of tiny ones. All well connected together. Oops. Oh, looks like in the stream we'll get to about exactly just having routed the power for this episode. But we have plenty more Saturdays to go. Yeah, I was talking to a friend, like, well, do you think you're going to run out of content? No, I have maybe a backlog of maybe 10 boards, and each is probably going to take multiple episodes, so I think we're good for the rest of the year at least. Depending on how much people like it. I mean, I have no idea how much people want to watch someone routing a PCB. Yeah, I didn't really promote it that much, so it's going to be kind of a cold start, which is good because there was a very non-zero chance that I was going to completely screw it up and not know how to do the stream, and it's just going to end in disaster. But I figured it out. I mean, thank you for giving me real questions and not just bots. That means I know that people can actually hear me and stuff, right? Okay, looks like we're looking pretty far now. Okay, so ground. Do I maybe want to route this on like this layer? Oops. Well, I guess I could just do it that thick. It doesn't matter. But I'm going to do it that thick the whole way just because otherwise it looks bad. Okay, yeah, we'll just do ground just so I can see where stuff is going. Something like that. I mean, the layer will obviously take care of it. If we look at the layer view, right, there's ground everywhere here. So let's take that back off so we can actually see stuff. Okay, 5 volts is going over there. I think I step it down to 3 right next to the network chip. I mean, okay, 5 volts is not that much higher than 3.3, and since it's an LDO, technically it's the same current anyway, so that probably is just a matter of taste rather than a matter of actual logical meaning. But yeah, it looks like we got this all going pretty well. Oh, those are the, yeah, okay, okay. I was wondering why yeah, the magnetics are, power over Ethernet, which is why 48 volts is connected to them too. Yeah, so I think we got power squared away. So I guess the next step is probably the Ethernet magnetics and the EMC of all the network connectors. So let's just grab one of these guys so that we can get into, okay, so that's too high granularity. That's just the plug itself. Okay, so this is the plug itself. This is the magnetics. Okay, but that was also just the magnetics. Oh, okay, so I got the center tap decoupling here. So where is the EMC for that stuff? Is it in here? Yes, it's in here. There we go. Okay, so this is a power over Ethernet controller. I guess there are probably going to be some people here without knowledge of what power over Ethernet is. So let's get back to drawing things so that we're all on the same page. So if we have Ethernet, 100 megabit Ethernet is going to be 2 pairs, one for transmit, one for receive. Oops, nope, sorry, wrong tool. Ah, screwing this up. Okay, so we have 2 pairs, let's say TX, RX, coming out of one side, right? These are going to be connected to, let's do this visual representation of a switch, right? You're going to have a switch on these things that can go to be driven in both directions, right? And so when sender wants to drive the output high or something, then current's going to flow like this, and then we have a magnetic core here and here, and then another winding around the core. That'll be the magnetics on that end, and then it'll go through the wire, through the Ethernet cable, and then you're going to have windings again on a different core on the other end. Let's draw the magnetic core green. And then you're going to have the same signal coming out the other end, right? So switching back to this red color, we've got current running like this, right? Which means we're going to make a magnetic field in our core, which means we're going to have current running like this, which means we're going to make a magnetic field in the other core, which means we're going to have, did I draw this the wrong way? No, I didn't. So we're going to have current running like this, and so that's how the signal goes through the line. Now, you can only transport energy for as long as you're charging the core, right? I mean, at some point, there's the core is the magnetic field in the core is not going to continue building up because it'll start to stabilize, and at that point, that's all the energy that you can do in that direction. Which is why it's good that network signals go on and off and on and off and on and off, right? So because you're sending bits at a high bit rate, you never actually saturate the cores. But if you were to connect it to some DC source, or maybe you have 2 different grounds on the different devices on either end of the network cable, then if it was just a normal communication line like USB, for example, then energy could flow through the cable. Potentially large amounts of energy could flow through the cable. It's called a ground fault or a ground loop or whatever. You can definitely fry electronics doing that if you connect two power supplies grounds to each other, then question is what is the ground of each power supply, and can it be different? And the answer is always yes. It's just a question of how much, right? And so yeah, I mean, I guess it's been probably 15 years ago now. I once designed a USB isolator, which basically took the USB signal and transformed it to magnetic signal, and then back to electric signal, so that you could both ends of the USB cable could be different grounds, right? And it wouldn't burn. But network has that built into it from the beginning, which is great. It means you can connect network cables across different floors of an office that are on different phases of the three-phase power, and no problems at all, right? So this also helps us a lot with EMC testing, right? If I were to imagine, let's say, I don't know if you guys can really see yellow, maybe we'll make it orange. If we have huge DC current, DC voltage swings on the wire outside, because, I don't know, let's say lightning, then that's all just going to be losses in the core. It's going to be, warm the core up a little bit, but those things are pretty big to begin with, as far as thermal mass, at least compared to it. I mean, they're tiny, but they're still big compared to the tiny resistors, for example. So we don't really have to worry much about things like surge or burst on a network cable. We also don't really have to worry about things like electrostatic discharge on a network cable, because, I mean, the part that's exposed to the outside is just the copper wire, right? You're not going to break that with ESD, right? And the ESD is not going to make it through the core. So yeah, so network is actually super easy from a electromagnetic compliance testing point of view. What makes it a little harder in our case is the power over Ethernet part, right? So the way power over the Ethernet works is the magnetics chip will have a center tap, so a connection to the middle of that coil, and then the middle of this coil. And if you think about it, no matter which direction the signal is flowing, right, the voltages on the outsides of the coil will change, but the center of the coil will not change in voltage, right? And so we could also make, connect the center taps of the two different pairs to different voltages, and it wouldn't matter, right? It doesn't interfere with the signal because it's in the middle of the core. And so if the top goes up and the bottom goes down, the middle stays the same. If the top goes down, the bottom goes up, then it stays the same, right? So we can actually connect DC voltage to the center taps here. Can't read my writing with this pen on the screen. Sorry. So that's 48 volts and ground. We could connect those to those center taps and then take them back out on this end, and it wouldn't mess with the data signals on the Ethernet, right? So that's awesome, but it also means that since power over Ethernet is newer than Ethernet, we could have had some termination on the device side that doesn't expect that voltage difference. And so on the controller side, on the side that switches it on and off, we have to do this sort of initialization dance where we put a small voltage on, we see how much power flows, put a larger voltage on, see how much power flows, and if it's like the exact nominal amount of power flowing that we know that the other side must be a power over Ethernet device, then we turn everything on, and it all works. And you can even, like, by varying the, if you go smaller voltage, larger voltage, smaller voltage, larger voltage, smaller voltage, larger voltage, like several iterations, and get a different amount of power flow each time, that allows the host to identify the power class of the device, right? So whether it's 13 watts or I guess it's normally 15 watts on the sender side, right? Receiver gets 13 because there's cable losses, blah blah. So that's like the standard original power over Ethernet, and then you have a bunch of higher power classes up to like 100 watts and more with newer standards. And yeah, so the host has to know what it should set its circuit breaker to, and by changing different strapping resistors in the device or the downstream side or whatever. I don't know if host device is really good terms for this, but anyway, uh, it can identify the power receiver and how much power it's expected to use, and so it can set up its fuse stuff accordingly. So we, as the power over Ethernet switch, are on the left side of this. We're providing power to devices connected to us, right? So since we're on the left side of this, we're going to have some switch on the 48 volts, which allows us to turn it on and off. And then we also need the whole initialization dance stuff. And since I don't feel like doing that in circuits, I'm just going to use a standard chip. That's almost always the right way to go if such a chip exists. So this is a power over Ethernet controller chip. It has 4 outputs, right? So you can see there's 4 MOSFETs here that actually do the switching, and each one of them has a power sense resistors here. R7 and R8 are there to allow the chip to measure the voltage drop over them, so you can see how much power is flowing through. And we got the gate of the MOSFET to turn it on and off. And then we have what is that, 90, no, R9 is the, a sense of what the voltage is on the output, which is probably mostly just error detection, I can imagine. And then we have a fuse, just to make sure that if the circuit's somehow screwed up and the output is somehow shorted, that nothing burns. I mean, technically everything's a fuse. Some things just do other stuff, right? But a fuse is actually, set up to where it'll, fail reliably in this mostly the same amount of power for the same amount of duration and whatnot, and also won't like smoke when it burns and that kind of stuff. So yeah, we got a fuse, and then we have just to keep high frequency noise off the lines, a capacitor, ringing and stuff. I mean, we could get into ringing later if people you're interested in sort of what kinds of things you have to watch out for if you have actual wires going outside of your box. That could be an episode if people want to understand that better, then just request it and I'll do it at some point in the future. But I mean, for a lot of this stuff, there's already good content on YouTube. I mean, the reason why I'm doing this stream in this sort of format is I learned a lot from watching other people. I mean, it's a lot more sort of a passive subliminal learning, like calibrating your gut feeling and stuff. And yeah, I mean, I was lucky to be able to watch people, and I would have been more lucky if I was able to watch more people. And so since the internet it makes it a lot easier for people to watch other people do stuff, I figured to just stream a bunch of stuff, and then people can watch me do stuff. And it's potentially more embarrassing because you're definitely going to find some errors and stuff that I'm doing and stuff that I don't understand properly, whatever. But yeah, I hope it's useful to someone. So, okay, so to make sure that we filter out any sort of higher frequency noise or ringing or that kind of stuff off of the line, we have our capacitor, and we probably should have put a voltage on this because this is another common problem. Oh, okay, so there is a voltage, it's just not showing on the thing. Yeah, I like to just show this so that people know that someone thought about it, because this is a common problem. Like if you put a normal like 16 volt ceramic capacitor or something that would be using in the rest of your low voltage circuit there, then it might actually work for a while and then die. And you really don't like those kinds of problems, because then you shipped stuff and then stuff comes back and whatever. And yeah, I mean, there are like three categories of problems. There's like the ones that almost never happen, and then there are the ones that almost always happen. And the ones that almost never happen, well, it almost never happens, right? And then the ones that almost always happen, well, you're going to catch those, right? It's the middle ones that are evil. And yeah, using the wrong voltage capacitor is definitely one of the middle ones where it might not fail on all devices, it might just fail on some, it might just fail after a while. Yeah, that it definitely want to be careful to use the right voltage capacitor on that, right? And so on these center taps going to the outside world, um, we do want to clamp them, but we don't want to clamp them to ground because they're switched to ground, which is why we have these clamping these clamping diodes to, just between the pins, right? Um, so I think what we want to do next is put all these clamping diodes down, because we have the same thing here as we had with the other clamping diode, that we definitely want them to be closest to the pin, and we want everything else in the circuit to actually flow through those. So, yeah, okay, that's just it's going to the center taps and not the pins. Well, I said that wrong, but so we probably have to put these down first. Wonder if there's like a good systematic way of where to put these down. Because if they're all in the same spot, hold on, let me check that these actually fit under the connectors, which I'm going to do in a very non-streamable way of walking across my office and finding one of the connectors and then putting it next to it. Oh, these just barely fit, so we don't want to put these under the connectors. I have one of these magnetics on a different design, and I have another connector here at the office, so it doesn't fit under the connector. So if it doesn't fit under the connector, then what do we do? How do we do this systematically? I guess we could put them between the connectors like this. And then I think I'm going to put the switch chip about here-ish. But then I'm going to run into problems way over there. Is this going to actually work? No, that's not going to work because that's not going to fit. But since I don't really have anything else going on down there, I'm sure I could just do this. We'll get the resistors working later. Oh, that's going to be fun routing those. Why did I screw that up that much? Oh, maybe it's... Yeah, but something like this, I think, is the way to go. Yeah, that'll work. Why are there lines on the board? Oh, because I copied too much from the other board that had the same dimensions. We'll take all of these lines off then. Okay. Yeah, I'm going to do I think I'm just going to explicitly put these outside the board so I don't think later that I put them there for a reason. They just kind of came with. Okay, so that's this one. Yeah, this should work, I think. I mean, I could switch around which port is what on the switch chip to make sure that I can route those. I mean, it's actually the switch chip has a bunch of snazzy stuff like it detects crossover cables, so if RX and TX are switched, then it still works. And so when routing, you can also then just switch them around. It makes routing more ergonomical. So I'm probably going to need to do that to some extent and jigger the ports around to where it's like this one and maybe that one. We probably want to do this one like starting here and then that one and then that one and then that one and then that one and then that one, like around in a circle. I'm not sure why these are like, it's almost like it's exactly the wrong way around. Yeah, well, we're coming up close to the end of the stream, so we're going to do that next time. But now that we've got those placed, then we want to make sure and put these in a way that everything else follows. So do I want to put them on the outside or the inside? I think I probably want to do that somewhat uniformly. That one being rotated that way, kind of. Yeah, it's weird. Different people have different tastes in how to put stuff down on a PCB and how things should be lined up and whatnot. And it's like, it really looks wrong if it's someone else's board. I'm not sure why that is, but yeah. I mean, having one rotated differently than all the others kind of bugged me. I guess it wasn't one, it was two. There we go. Okay. Yeah, I think I'm just going to put them to the outside of the board because then I won't have them in the way on the inside because that's where all the network signals are going to be going. I guess I probably, wait a minute, what? Oh, because it's not that guy's one, it's this guy's one. Okay. Since it's not actually ground, since it's the switch thing, they don't all have the same destination. I mean, one side is always going to be 48 volts, and then the other side's always going to be something different. So I guess if I do it this way, then where do I put the capacitor? Probably just right next to it. I mean, I want to make sure that the capacitor is not going to get the higher voltage. Same thing as the same thing as over here, the example I brought earlier of clamping diode going first. It's actually going to be a lot less important with the magnetics because there's already an inductor in between you and whatever's messing with you, right? And that's going to be some DC voltage resistance, but it's also going to be a lot of magnetic resistance, especially with transient lines. That's a steep edge of voltage, right? And so the inductive resistance is going to be going to protect us from most of stuff, right? So yeah, it's not as much of a problem here. So why? Wait, where's the capacitor that fits with this guy? Oh yeah, there we go. Oh, there it is, way off somewhere else. Okay, I think I'm just going to do 48 volts just as a track along the bottom here. Can I fit a 1 millimeter track under there? Yes, it fits perfectly. Well, why don't we do that? And then over here we can go. There's not going to be a whole lot going between these things, so I can get away with it being on the top layer here. That'll just be the boundary to that part. Oh, I guess I didn't uniformly place them with the same. That was too close to the edge anyway, so this will be a good way to keep me honest with my distance to the board edge. Distance to board edge with components is also a pain. Like sometimes the manufacturer will manufacture you a board several times with your distance to board edge, and then they'll get a new machine or something, and then they'll, hey, yeah, we can't manufacture that anymore. And it's like, yeah, but like I already, The guy that designed that circuit moved to Denmark and doesn't work for me anymore. And why didn't you notice that earlier? It's like, oh yeah, well, it used to be a problem. It's like, oh man. Yeah. So I've learned to respect board edges a lot more than when I was just a uh, young and wild engineer and didn't know better. Okay, so these are going to be in pairs. We're going to get into the, how to lay out the, um, higher frequency Ethernet lines probably next time. Um, Higher frequency is relative. Like, 100 megabits is, I think, 125 megahertz, which is because with Ethernet, I guess they didn't like count the overhead. And it's kind of weird that it's a different frequency than the nominal megabits. Like USB is 480, or USB 2.0 is 480 megabits and also 480 megahertz. Sounds logical. Whereas Ethernet is like 100 Mbit Ethernet is 125 megahertz. Um, but yeah, that's actually, I mean, at least in this day and age, no longer like super high frequency. Um, so yeah, you can get, wait a minute, why is that? Ah, okay. Yeah, I'm gonna, no, so that's not good the way that is. But I'm probably getting ahead of myself with these. Why didn't it do that one? I did UU. I got the rest of it anyway. So I guess we probably want to do something like, just to get them somewhat parallel. I mean, the thing with the M12 connectors is uh, the pairs are actually opposite pins, which does mean that you can mirror the connector without it causing problems, but it does make it like really annoying to try and route lines that are the same length to both of them, right? Which you kind of want to do with Ethernet. So this one's going to be, we're trying to make it as long as possible so that it's somewhat the same length as the other one. But yeah, we'll get into why that is later. But yeah, this looks like kind of the strategy that I would want to do for all of those connectors. And then, yeah, and so I guess, wait a minute, where am I going to put the power over Ethernet stuff? Am I going to maybe move these more to like here? And put power Ethernet here down in the corner? Oh, that's already all laid out in the right way. That's cool. When did I do that? Yeah, that'll fit. That'll fit nicely there. Yeah, so looks like we got one more minute left. Thank you for coming. Wasn't a whole lot of people this time, but I didn't market it much either. So we'll see how many people come back next time. If we have maybe more questions next time. I had fun, and I hope for any kind of feedback, good, bad, whatever. And if there's anything you want explained, even if you're not watching this live, if you want something explained, then just, yeah, send me a message on X, maybe reply to the stream or a future stream, and I'll try and answer your question then. I certainly don't know everything. I'm sure there's some things that I kind of, in some esoteric ways, did wrong, but I actually have not failed EMC testing yet in my career, so I must be doing something right. And yeah, so I hope to have helped calibrated your gut feeling about how important different things are relative to each other, and also introduced maybe some common pitfalls that I've seen in. I mean, I've trained a lot of engineers as well, so I mean, not formally, but kind of on the job, like do this differently and whatnot. And yeah, I hope it was useful, and I hope to see you guys again next week. Now I just have to figure out how to turn the stream off. For one, it's going to allow me to share some knowledge, my 25 years of making circuits. And another advantage is it will give me a deadline to actually finish some unfinished project. Gotta have the fear, right? So I'm going to be routing several boards over the next couple of weeks. And as far as the format goes, um, please ask any and every question you might have in the chat. I don't mind being interrupted. If it's a little off topic, I'll probably answer it anyway. If it's very off topic, I might move it till the end. And we have a good 2 hours of routing time now. So let's get started. What we're routing today is a network switch. Right? These large connectors are M12 connectors. They're basically Ethernet for an industrial setting. So they have they're screwable, so they can't like wiggle out or fall out. They're very robust. They are usually waterproof, which is one of the reasons why we're using them here, because waterproof usually also means dustproof. We have one power connector down here in the bottom right hand corner, and all the rest are Ethernet connectors, except I believe this one's special. We have 7 that are connected to a switch chip, and then 1 that's going to be connected to a land grid array on the back side, and so we can put different circuits on the back side depending on what we want to do. We could, for example, put just a jumper circuit that would make it from a 7-port hub with one weird one to an actual 8-port hub. It just jumpers the connection across. Maybe I should switch to the circuit to show you guys this better. There we go. Go up to top level. Okay, so we have, let me make this wider for you guys. So we have the switch chip here in the middle with all of its connectors, and you can see one of the ports of the switch chip is going here through a PHY to PHY connection, which is basically just so that you can connect to Ethernet to get things together without actually using magnetics. We can look at that in more detail if someone's interested. And we have, so that's going into the compute sheet, which is going to be the land grid array. And so we could just jumper that to this, and then it becomes a normal port. We could also put something else on this land grid array, meaning that, for example, we could put a Raspberry Pi compute module on there. That's actually a concrete thing that we're working on right now, so that's why I'm routing it. You could also theoretically put some other kind of switch management. You can see we have the I2C bus from the switch chip going into there, so you could put some microcontroller with that's connected to Ethernet, and then you could talk to the microcontroller and tell it to, I don't know, set up VLANs or be a time server or something like that, right? In which case you probably would just leave out that one M12 connector. So the concept of the whole thing would be basically a 20-year-old 100 Mbit switch, but waterproof and robust, and you can put it outside and you can put it in harsh environments and whatnot, right? So that's the whole idea. Oh, I'm getting a bunch of spam bot messages. I'm gonna figure out how to turn them off next time. Anyway, so let's switch back to the circuit view. So I already placed the M12 connectors because that's kind of finicky and probably not fun to watch. But basically the trick is if you select them, click E. Oh wait, that window's going up where you guys can't see it. Hold on a second. Click E, and you get the properties of it. I'm not sure if that has to do with German developers on the KiCad team, E meaning Eigenschaften in German. Uh, but anyway, so E gives you settings, and then you can put the X and Y in there, and that's good for spacing things precisely. We have, the connectors are should be 32 millimeters apart across the board. And I also kind of generally grouped things. I guess if I could do a split screen, I can show you guys why KiCad is cool. Let's do that on this side, and then that on this side. And if we go, oh, this is kind of, I had to make my screen smaller for the stream, so this is kind of annoying. But let's say we click on this hierarchical sheet that has the switch chip, and here you can see that it highlights all of the switch chip components. If I go to the PHY to PHY, then okay, that's all the PHY to PHY components, right? So you can use that to kind of generally group them. I already kind of grouped things in, and what we're going to do next is we're going to start with the EMC relevant stuff, right? There's not a whole lot of, I wonder why those little markings are on the PCB. If you select the layer, it sometimes works better. There we go. So the hard part of PCBs is EMC, which means electromagnetic compliance, which basically means, if lightning strikes near you, you're not allowed to break, and you're also not allowed to emit enough interference to mess up other devices. Right? So I guess technically for most things you certify compliance yourself, that you're not doing any of the bad stuff, and but for, if you have an antenna or something, then you're going to have to actually get it tested and get a number from the FCC that you're a compliant device and whatnot. But in reality, it usually means that you, if you're a contract developer or something, I mean, most, at least not most maybe, but many companies sub out their circuit design work to freelancers or other companies like us. And so you want to prove to your customer that you didn't screw it up, because at the end of the day, it's going to be their name going onto it. And so most circuits, most stuff that we ship does get tested in an EMC lab. And so they'll have a big room where they're isolated from the outside world. It's a big Faraday cage, and they'll have your circuit run, have antennas around the room to see if you're emitting something in a stronger, stronger signal than you're allowed to. And they'll also try and break your device with different means, right? So that they have a little ESD gun that'll simulate people touching your circuit and shocking it, or they'll have a surge and burst tests, or on for the power lines, where it's kind of simulating a lightning strike somewhere close. And depending on what standards you're testing to, those will be stronger or weaker. There's also some stuff that's usually not relevant to normal electronics, like magnetic fields or whatnot. I mean, maybe if you're making medical devices that have some solenoids or something in them that also use magnetics, well, maybe that's interesting. But for this circuit, we can ignore the magnetic field testing part. So we have in the schematic, we have a portion. We have input power connector, and then because people in industrial settings are very good at pinning things wrong, and this is probably going to be wired by somebody to like a battery or something, and So there's a high chance that they could get it wrong. And since we have, well, nominee 48 volts input, it's usually more like 60, or 55 or something if you're using batteries, because battery voltage is usually higher than the nominal battery voltage. And power supplies often do a similar thing, just to be similar to batteries. So since we have nominally 48 volts in, we're not going to have a whole lot of current flowing through here. The Raspberry Pi compute module is something like 5 to 10 watts, depending on what you're doing. 5 to 10 watts at 48 volts is not a lot of current, right? So it's not actually all that expensive as far as power for us to just do bridge rectifiers, and they're certainly not expensive as far as chip costs. It costs like pennies, 6, 7 cents. So if we put those in there, then nobody can screw it up, right? So after those two, then we have our, I just called it EMC because that's what it's doing. It's, make this bigger so we can actually talk about it. First part of the EMC, and this is if you want to copy this, this has gone through testing successfully for both consumer electronics as well as things like rail infrastructure. There's higher compliance levels. Yeah, so we have a big TVS diode, the transient voltage suppression. Basically what this diode does is just start conducting if the power across it is above some certain nominal voltage. This is 64. You got to watch out because these things have tolerance. So if you have, nominal 48 volts in, then you definitely want considerably more nominal clamping voltage on your diode, because if your diode's 10% low and your input's 10% high, then they might meet each other, right? Often these diodes actually if you have enough power going in, they can destroy themselves. And TVS diodes are set up so that their fail is a short circuit. And so even if they do fail, then they'll just melt themselves together and still keep clamping the input voltage and saving the rest of the circuit. So yeah, so if you have electronics that for some reason died, often just taking off the TVS diode makes them work again. I mean, you may want to replace it with a new one, but yeah, that and capacitors are the reasons why most electronics die. So yeah, that in this case, we want to make sure that if we're in a surge or a burst test, or if lightning actually does strike close to us, or if somebody connected it to the wrong thing, that we just clamp the input voltage to save the rest of the circuit. Then we also want to filter out potential high frequency noise, or any noise really, but low frequency noise is usually not so much of a problem. High frequency noise, like maybe we're next to something. I mean, in the industrial setting, one of the reasons why you got to watch that for that stuff is, in an office, say, everything has gone through compliance testing individually. And so if you're on an office desk next to something that has gone through compliance testing, then chances are that it's not going to be giving you a whole bunch of electromagnetic interference. But in an industrial setting, if you're in a machine that's a big metal box, then they only have to pass compliance testing for nothing coming out of their box, right? So they might have components in there that wouldn't pass like at all as an office device, but since it's within their machine, they're going to be they could be interfering with you because they're screwed in next to you, right? That's technically their fault, but that's not a lot of fun explaining, right? And the other thing is, in industrial settings, people weld. And welding is electromagnetic interference on steroids, right? And sometimes they expect you to actually still work while somebody's welding somewhere close to you, right? Especially if you're I mean, we don't have components in welding robots yet, but we may. I got a question. Sorry, I joined a bit late. Is this testing individually? And so if you're on an office desk next, but that's not a lot of fun explaining, right? And the other thing is, in industrial settings, people weld, and welding is electromagnetic interference on steroids, right? And sometimes they expect you to actually still work while somebody's welding somewhere close to you, right? Especially if you're, I mean, we don't have components in welding robots yet, but we may at some point, right? One of these might go in there, and so these next two capacitors are just for filtering out electromagnetic interference coming from outside. They also, technically filter stuff from, coming from us going to the outside, but we're not producing a whole lot. We'll get into that later when we see the power circuit. And then we have the Worth inductor. This is a choke, right? Which basically means it's got both wires wound around the same core. So if we have power flowing this way and power flowing this way, then the two magnetic fields are going to cancel each other out, mostly because the wires are very close to each other, and we won't actually have to go through all the magnetic momentum of spinning up the field in the core, right? So energy flowing, power flowing in and out in the same amount will pass through easily, but common mode, right? So power flowing in on both lines, which is, for example, the burst test is basically just testing that. Right? So let's imagine the wire that's going into this box is going through some cable channel, and there are other cables in that cable channel that go outside and got hit by lightning, right? That's kind of what they're simulating with the burst test, right? Or maybe it's, you hit the power lines, it blocks down the street, and you're still getting some of that, right? Yeah, I got a question. Sorry, I joined a bit late. Is this KiCad? Yes, it is KiCad. I love KiCad. Maybe in some later episodes we can get into why KiCad is basically superior to everything. It's almost as good as the expensive CAD software, but it has the advantage that it's free. It's also an advantage, I guess licenses for CAD software have come down some. Like at the beginning of my career, it was like, I don't know, 40 grand or something if you want to do PCBs professionally. And I guess it's long enough ago that I can say thank God for being able to hack stuff, or I would never have been able to start my business. But oh, and also, sorry, there's a bit of delay. I wasn't ignoring you. It just it takes a bit for the comments to actually go through the system, and then the stream's also on a delay, and so that's why it takes a little bit for me to answer. But ask away. I love the questions. So KiCad is free, which is good because that saves you a lot of money, but also it's good because it allows you to share stuff with other people, especially young people entering the field, open source projects, that kind of stuff. Like we have about a continuous